graphs of a polynomial function. First, let's consider intrinsic features of the graph of a polynomial function. The graph of a polynomial function is, first of all, continuous. Continuous meaning connected. Sometimes it's good to write here all in one piece, right? It's equivalent. So always connected. All in one piece. What does it mean, Professor? Well, it means that if you graph your polynomial function, you expect perhaps a parabola-like function, right? The parabola-like. And notice I on purpose drew here some wiggling. Eventually, it will show a parabola-like shape, right? But in the middle, probably some ups and downs. We don't know, right? But it has to be, no matter what, connected, all in one piece. All in one piece, right? Cannot be broken. That's what it's saying. Another example, maybe when you graph your polynomial function, you might get a chair-like function, right? Chair-like, like this, eventually, right? But what is important is that has to be connected, all in one piece, cannot be broken, right? Cannot be broken. Perhaps you may get something like this, but all in one piece. This is what it says, continuous. Second feature, smooth, no sharp turns. Turns out the graph of polynomial function is smooth. What is smooth, Professor? Well, means no sharp turns, no corners, no things like this, right? No cusps, no corners. Maybe I should write between parentheses. No cusps, no corners. When you graph a polynomial function, you will never see corners. You will never see these kind of things, right? No sharp turns. If it helps, think of the shape of a highway. Think of the shape of a highway. You know, when you're driving a highway, imagine if a highway will have this shape. Something bad will happen to the cars at high speed, right? Yeah, no good, no good for a highway, right? Highway is smooth, smooth. Yeah, this is what the second property is for the graphs of polynomial functions. Third property, either parabola-like or chair-like, just those two shapes. Either it will look like this, maybe opening downward, or maybe like this, or maybe like this, but that's it. No other shape, no other shape. You may say, Professor, but what could be another shape? Well, for example, what if they give you the shape of a bell like this? Bell shape. Right here, it's important. This bell shape is seen a lot in statistics. Turns out that is not the graph of a polynomial function. Bell shapes not good for graphs of polynomial functions, okay? It has to be either parabola-like or chair-like. There will be an exception. I will talk about that later, right? Yes, it's bell shape, no good, right? No good. Not the graph of a polynomial function, right? Not the graph of a polynomial function. I tell you this, guys, because on the homework, you will be given a bunch of graphs and they will ask you, right, what could be the graph of a polynomial function? If you see a bell shape graph, no, this is associated to a different function that you will study in calculus later in statistics. But it's not the graph of a polynomial function. Now, exceptions. It could be a line if the degree of the function is 1 or 0. You know that if you are dealing with a linear function, right? A function of degree 1, let's say y equal to x. Of course, you're going to get something like this, right? Y equal to x. This is a polynomial of degree 1. Because of that, you're getting a line. But if the degree is greater than 1, you will get either parabola-like or chair-like. Another example where you will get a line, well, if the degree of your function is 0. Degree of function 0, professor? Well, something like this. Y equal, for example, the number 3. It's a constant function, right? And its graph is just a line, right? This is what they're talking about. So, conclusion, guys. The graph of polynomial functions could be chair-like, parabola-like, or perhaps a line, right? If the degree is 1 or 0, but never a veil, never a graph showing corners, never a graph showing cusp, or never a graph that is broken, right? Separated in 2, 3 pieces. No. All right, so for you to enforce this, I'm gonna give you a bunch of examples here first, and then you will have to do it on the worksheet. Is the following graph the graph of a polynomial function? First, number 1, look at this. Look at this. Let's check, right? Is this continuous? Well, you see all in one piece, so checks continuity, right? Great. Is this smooth? Well, looks like the shape of a highway, right? It's smooth, right? And so this is good. Is it parabola-like or chair-like? Yes, parabola-like, right? Resembles a parabola, right? Eventually look like a parabola, right? For big values of x on the right, for big values of x on the left, right? Resemble a parabola, so this checks. Parabola-like. This doesn't apply because it's not a line, right? So then this is the graph of a polynomial function. So the yes, right? Parabola-like. Very good. What about this? Number 2, is this the graph of a polynomial function? Anybody in the chat could say number 2. Mm-hmm. Well, guys, if we check the conditions for this to be the graph of a polynomial function, look, continuous. It must be all in one piece, right? Look at this. Doesn't follow that, right? Yeah. Broken, look, gap. So no. Not connected, right? Not connected. Right? Because of that is not, is it smooth though? This is smooth, but it's not all in one piece, right? Because of that, not the graph of the polynomial function. What about this? Number 3. Is this the graph of the polynomial function? Well, look at this, right? All in one piece, checks continuity, right? Connected. Smooth, right? Looks like the shape of a highway, right? Parabola-like, no, but chair-like, right? Chair-like, so let's check this. All right, so then it is the graph of a polynomial function, right? So this one, yes. Very good, chair-like, right? Yeah, and try to remember these guys when you go over your homework. You will be given a lot of shapes. You will have to determine which ones qualify for the graph of a polynomial function. All right, so I wanted to practice on this first before going over the generalization of this. So try to do this, guys. These are all doable, very nice exercises. So try to figure out if the graph that you are looking at here is the graph of a polynomial function or not. Yeah. And very good, very good, very good. And if possible, write there the justification of why it's not a polynomial function, right? Yeah, great. Jing, great. Excellent, excellent. Jing, if you don't mind, could you write on the chat why this is not the graph of a polynomial function? What's wrong with this for it to be the graph of a polynomial function? Or you can say, yeah. Very good, Jin. Jin saying because it is sharp, right? It's a sharp turn here, right? A sharp turn, which we can call also a corner, right? Corner, sharp turn. This is not good for the graph of polynomial function. We said polynomial functions, when graph, they show smoothness, right? They are smooth. They look like a shape of a highway. This could never be a highway. Look what will happen to the cars going at a high speed there, right? That corner, no good. So no, very good. What about number 2? Try number 2 now. Is this the graph of a polynomial function? Give it a shot. Yeah, notice this guy goes up forever, this guy goes up forever, right? Yeah. I can see. Jing. Excellent, Jing. Great. Now, what's the justification? Why is it the graph of polynomial function? Could you write it on the chat or you say? Well, let's check the conditions, right? One says all connected. Yes, it is all connected, right? All in one piece. That's good. Then a requirement for this to be the graph of a polynomial function is that it should be smooth. It should resemble the shape of a highway. It does, right? It does. It's smooth. It's smooth. There's no sharp turns, no corners, no cusps. Third, it should resemble either a chair-like or a parabola-like. This looks like a parabola, right? Parabola-like. Parabola-like. Very good, very good. Right? So good. Yes. What about this? Number 3. Check that out, please. Then we'll move on. Let's check. Lucero. Very good, very good. Excellent. Yeah, Lucero, do you mind to type on the chat or to say verbally why is not, what is wrong with this for it to be the graph of polynomial function? Why is not?
Yeah, it's not connected.
Not connected. Excellent, excellent. Great, great. Yes, that, right? Not connected. Look, it's in 2 pieces. You will never see this broken graph when you graph a polynomial function. This is what they're trying to emphasize here, right? It will be always connected. Yeah, again, guys, thinking of the shape of a highway, I think it's a good one because a highway will never be broken, right? It's continuous. All right, so this, yeah, very good, guys. Now, let's try to look at this part, but for that, I have to talk to you about the 4 scenarios now in general. If we go back to the notes, you will see here the mathematicians, based on the 4 scenarios for the graph of power functions, they figure out 4 scenarios for the graph of polynomial functions and behavior of polynomial functions. Recall that the leading term determines the end behavior of the polynomial functions, right? So just like we got 4 scenarios for power functions, for polynomial functions, we will get also 4 scenarios. If the leading coefficient, remember that the leading coefficient, the coefficient of the leading term, right, is positive and is even, right, like 2, 4, 6, 8, then it will resemble a parabola, right? It will be a parabola-like shape. But in the middle, notice that they don't show what happens in the middle. In the middle, you may have some wiggles, some ups and downs, right? But the end behavior will be rises to the left, rises to the right, right? And this is expressed using the arrow notation, right? If X increases without bound, approaches infinity, then Y also approaches infinity, it grows. This is what it is saying. Here, if X approaches negative infinity, right? Negative infinity lives here. Then f of X, the output value, approaches infinity, right? Which is here. Minus infinity here, infinity here. Good, right? And similarly here, right? If the degree is even, but the leading coefficient is negative, then it will resemble a parabola that opens downward, right? Notice that in the middle, many things can happen, right? But eventually, for big enough values of X, this will fall. For big enough absolute values of X, I would say, right? Because this grows negatively, this will happen. It will fall to the left, it will fall to the right eventually. And this idea of eventually, you have to kind of understand it because later on it will be used in calculus. All right, similarly here, right? The other scenario is if the degree of your polynomial function is odd, such as 3, 5, 7, 9, right? When you graph your polynomial function, it will resemble a chair, an increasing chair if the leading coefficient is positive. Now in the middle, look, I have drawn this wiggling here, ups and downs perhaps, but eventually it will fall to the left, eventually it will fall to the right, right? For big enough values of X, big enough values of X here in the negative direction. All right, so similarly here, right? If your degree is odd, the degree of the polynomial function, and if the leading coefficient now is negative, you will have a decreasing chair for the shape of the graph of your polynomial function. Eventually will rise to the left and eventually will fall to the right. Here again, using the arrow notation, if X grows without bound towards infinity, then f of X will grow, will decrease without bound towards negative infinity, right? This is what this is saying. And equivalently, if X grows or goes to negative infinity, approaches negative infinity, f of X, the output values will approach positive infinity, right? Grow without bound. So this is what it's saying. Okay, guys, so now try to keep this in mind, right? Let's look at how you can figure out this. Can you figure this out? It says use the leading coefficient test to determine the end behavior of the polynomial function, then use this end behavior to match the function with the graph. So let's show this, right? But let me see if I have in the notes something better. Yeah, it's very good. Yeah, let me show you this. Or we can try perhaps. Yeah, try to do this, right? Again, the whole idea is to look or to pay attention to the first one. So look at this. And from there, try to see which one is the graph. Now, this time they give you the end behavior in words, but also they show you a graph, right? So you may help yourself by looking at the graph. So, let's see. Yeah, very good, very good. The first term, the leading term, is the one that determines the end behavior. Jing. Let me check. Number 4. Jing. Yeah, you made my day. Excellent, excellent. Yeah, very good. Jing is saying, right? We have this leading term, right? Leading term, which is showing odd degree for the exponent, right? On degree. So quickly we think of a chair-like graph, right? Chair-like. And this is negative coefficient or negative leading coefficient, right? So we think of a chair, but not the increasing chair, but the decreasing chair, because this guy is negative, right? So we think of this, right? Now, in the middle again, guys, could be ups and down. We don't know, right? We don't know what can happen in the middle, but this eventually will show this, will show that. So rises to the right, falls to the left, right? To the left. Yeah, this is what matters. Right, so which graph is showing this? Look, this guy is not showing a chair like, it's showing a parabola like this, perhaps. This is not a chair like this or this, right? But look, which one is showing this? This guy, right? Look, eventually rises to the right, eventually falls to the left, to the right, right? Eventually rises to the left. Be careful, guys. This is right, and this is left. Left to right. Yeah, very good, right? So this, and again, this wiggling, you say, Professor, there's a wiggling here. Doesn't matter, right? Could go up and down, but eventually is what matters, right? Eventually we'll show this, right? This should match with this. Maybe I will use these two guys, very important. Look, you have to make this match. You have to make this match. This is what matters. What happens in the middle, not relevant, right? For the end behavior. Very good. So this tells us that this guy is this, right? Yeah. This was with a graph, right? But now let's see what happens with this if they don't give you a graph. But we did this once before, right? So, but I want you to check this out. This one here. Yeah, try this one, number 9. Yeah. What? Work on this, please. Figure out the end behavior and therefore the graph, right? Yeah. Use the leading coefficient test to determine the end behavior, right? Of the polynomial function, then use this end behavior to match the following with its graph. Hint, as usual, guys, hint is this. Extract the leading term, right? Work with this guy. This will tell you, right? Very good, very good. Work at that guy. This is number 9. Very good, very good. Lucero, very good, very good. Savannah also, great, great guys. Good job. Yeah, good job, great, great, great. Very good, right? If we analyze the end behavior of the leading term, right? Turns out that will tell us the end behavior of the whole polynomial function, right? That's something that mathematicians figure out. Notice the degree is even, so even degree. So immediately we think of a parabola-like function, right? Parabola-like, and this guy is positive, positive. So this is telling me that the parabola, to be consistent with happy face, should open upward, right? Upward, right? Happy face, remember? Upward. So we look for that quickly, right? Cannot be this, it's a chair-like. It cannot be this, it could be either this or this, but quickly, since you see this up open, the parabola opens up, it has to be this, right? It has to be this. And clearly, right, if rises to the left and rises to the right, right? Both. So rises to the left and rises to the right. So this guy, right? You follow us? So, and you may say, Professor, but there is a wiggling here, a wiggling. Yeah, expect these wigglings, right? Ups and downs in the middle here locally, right? Locally, but globally, right? Kind of eventually, right? This will end up in this direction, right? Up, and this one up too. Great. All right, so this was that. Now we got to talk about the zeros of the polynomial functions, right? Yeah, let's talk about that slowly and nicely because this gives a lot of trouble to students. So I'm gonna do this now. Okay, zeros of a polynomial function. What are the zeros of a polynomial function? Definition. A zero of a polynomial function is a number that when plugged into the function makes it equal to 0, right? Makes it equal. The evaluation gives you a 0 output value. That's called a zero of a function. Now, mathematicians figure out 3 steps in order to find the zero of a polynomial function. This is a basic algorithm, right? We're going to go over this first, but there are other algorithms whenever this algorithm is not strong enough to find the zero, right? But first, we should start with this basic algorithm. Later, I will show you more sophisticated methods. All right, the method says, right, based on the definition, right, set your polynomial function, whatever it is, equal to 0. Then factor your polynomial function between parentheses I'm writing here if possible, because you know that factorization is not always possible, right? And then you can see quickly, readily, the weakness of this method, right? Relies on being able to factor. Right, next, set each factor containing the variable, let's call it x, equal to 0. Maybe we should write in general the variable because sometimes the variable might not be x, might be t, might be w, right? Containing the variable. The variable here, containing the variable. For example, x. Right? For example, that could be any variable. equal to 0. And from there, you should be able to extract the zeros of your polynomial function. Let's see an example here. Nice and slowly, we're going to do this example, okay? You will have to recall some stuff that you learned before in previous courses. All right, so it says here, find the zeros of this polynomial function, x cubed plus x squared minus 42 times x. How we find the zeros of this polynomial function? Well, let's follow the 3 steps, right? That were suggested. The first step says, whatever the formula for your polynomial function is, set it equal to 0. Set it equal to 0. We need to know for which values of x this function is equal to 0 when evaluated, right? Next step, remember, was factor, right? First, set it equal to 0, the polynomial function, second step, factor if possible. All right, to factor, I want you to notice the following. This polynomial function contains the variable x as in each term, right? Look, the first term has an x, second term has an x, the third term also contains x. So I'm going to factor out then x, right? X. Yeah, we said this factor out. This is factor out x right here. Factor out x between parentheses, which is the GCF, right? Greatest common factor x. Yeah, x out. If x is out, what is left? Well, x into x cubed is going to be x squared, right? Remember, when you divide 2 powers, you subtract the exponents. Invisible one is the exponent here. Subtracted from 3 is 2. Plus, 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 plus. X into x squared now. X raised to 1. So this is 1, this is 2. Subtracting exponent 1, right? Minus, minus. X into negative 42x. X and x, they cancel. Negative 42 stays. This is it, right? This is it. So x times x squared plus x minus 42 equals 0, equals 0. This is what you get when you factor out x, all right? Now, guys, remember, in previous courses, they showed you how to factor these quadratic trinomials, right? You write x here, and you look for 2 numbers whose multiplication is negative 42 and whose sum is this invisible 1, right? You do some trial and error there. After some trial and error, you will discover that those numbers are 6 and 7, right? 7. One of the numbers must be negative for the multiplication to be negative. The one that has to be negative is this, because you want the sum plus 7 plus negative 6 to be 1, right? To be 1. So you're okay with this factorization, guys? Okay. Now the third step says set all factors contained in the variable, right? Look, this x plus 7, this x minus 6, set them equal to 0. Set them equal to 0. So this is what is next. X equal 0. And you can readily see that you got the first 0. X plus 7 equal to 0. And x minus 6 equal to 0. This is the first 0, x equals 0. From here, minus 7 on both sides of the equation leads to x equal minus 7. This is going to be your second 0. Plus 6. After canceling these 2, x equal 6 is going to be your third 0, right? Your third 0. Right? Very good. So now mathematician, they kind of put this together by saying zeros of f of x, the function, right, are, and then they just say 0, comma, negative 7, and 6, right, 6. Now, I want you to catch this. there is a connection between these zeros and the X-intercepts. Then since the output values of these guys are clearly 0, right? Because when you plug 0 into the function, you get 0. These three order pairs, 0, 0, minus 7, 0, and this 6, 0, they all lead to 0 when evaluated. These are going to be the X-intercepts, are the X-intercepts of f of x, right? X-intercept of x, professor. Wow. Well, I want you to see it. If you go to your Desmos graphing calculator and try to catch these guys, because there is one question on your homework that will not allow you to do factorization. And it says in the instructions, use the graphing calculator to answer that question, right? So you do this, what I'm doing now. Look, if you cannot factor, right, for some reason, on your Desmos graphing calculator, do this. Y equal x cubed plus x squared minus 42x, right? The graph is this, right? The graph is this. So you can see that where the graph, look, you have to make it really smaller to see the chair-like shape, right? The wiggling is very, very, very pronounced here, right? Look, up and down. But then you can see the main shape, right? Is still a chair, an increasing chair, consistent with the fact that the leading coefficient is 1x cubed. Now, but what is important, what I'm trying to catch here is this. When you look at this graph, guys, notice that this guy, when you click in here, is showing the -7 there, right? Look here, this is this, right? It's the X-intercept. Where is the 0, professor? Here, 0, right? And where is the 6? Here, right? 6, 0, minus 7. They are the X-intercepts, right? So try to catch this, because in the homework, in one question, you will have to do this graphing, and you will have to approximately catch the X-intercept from the graph, right? From the graph. Great. Very good, guys. So this is how this works. The zeros are the X-intercepts, right? That's the connection with this. All right, here is another exercise before I send you to do something, but probably you should practice first, right? This is another form. Practice here, practice makes the master, so practice here. Can you do number 10? But 10 is just the one that we did, so number 11 is better. This one. This one. Right? F of x is x cubed minus 10x squared plus 25x. Hint, step 1, set whatever the formula is for your polynomial function, set it equal to 0, right? So start there and solve for x using factorization, right? Step 2, factor. Right? Factor, and then set each factor equal to 0. From then retrieve your solutions, right? Yeah, great. Yeah, very good. Yeah, very good, guys. So let me script. Yeah. Aha, Jack. Excellent. You got it. Yeah. Very good. Excellent. Yeah, very good. It's tricky, right? Remember, as the example that I did before, right? If 0 is one of the solutions, you must include them as part of the solution, right? It's also a solution, yeah. Mm-hmm. Yeah, very good. Excellent. Yeah, it's tricky. It's a tricky problem. Yeah, and it will allow me to mention something here. Okay. let's do it together, right? Let's do it together. Tricky question. More students are posting answers. Good. Jing, close, but notice that I think one of the roots is repeated. One of the zeros is repeated, right? And there is this also 0. So it's tricky, Yeah, but let's see. Yeah, try to refine it. Try to improve it. Okay, so step 1 says set the formula defines your polynomial function equal to 0. Step 2 says factor. We're going to factor out x because x is the GCF, right? The greatest common factor or greatest common divisor, x. So x out, inside, what is inside? X into x cubed, x squared, minus, x into 10x squared. Notice x into x squared x, so minus 10x, and plus here x into 25x, x cancels, 25 stays, right? Plus 25. But now, remember in previous courses, you learned how to factor these quadratic trinomials, right? It's sort of doing this FOIL in reverse, right? We look for two numbers whose multiplication is 25, whose sum is -10. After some trial and error, you will figure out that this is 5 and 5. But the sum, I want it to be -10. So this has to be negative, this has to be negative, right? -5, -5. Great. Now step 3 says set the factors containing the variable equal to 0, right? Step 3. Step 3 is this is one factor containing the variable, you set it equal to 0. This is another factor containing the variable equal to 0. Another factor containing a variable equal to 0. Here is the first 0 of the polynomial function, right? Adding 5 to both sides will give you the second 0, right? X equals 5. Adding 5 to both sides, x equals 5 again. Professor, isn't it repeated? True, right? These two guys are the same. So what mathematicians do is this. The zeros of f of x are, they will say, right? Are. What are the zeros? 0 and 5, right? But in order to say that this 5 is repeated, they will say and 5 with multiplicity 2, with multiplicity 2, because it appears twice, okay? Try to catch that, guys. Multiplicity means how many times this appears, this factor appears in the factorization, or how many times you get a 0, right? Twice, right? It's repeated, this 0, right? So that is identified with this multiplicity 2. When the 0 appears only once, you don't have to say multiplicity 1. Mathematicians just post it, right? But when it appears twice or 3 times, you have to specify the multiplicity. In this case, 5 with multiplicity 2, right? So otherwise, just mathematicians will write this as x equals 0, x equals 5, right? Yeah. And as you can see, this is the reason we have to choose this, right? Choose this. You follow, guys? This is 1, 0, but multiplicity 2 appears twice, right? -5 is not a 0, right? You see? Yeah. So this is not good. 5 is the one, right? But it's just that appears twice. Be careful there. Okay. Now let me show you how to deal with this other form, okay? Our form, let's go back to a lecture. Now that we have an idea how to deal with multiplicity, let's go back to this other form. Suppose they give you this, guys, now. Find the zeros of f of x equal x cubed plus 3x squared minus x minus 3. 4 terms now, right? 4 terms now. So we gotta be careful there. Now, step 1, set the formula that defines your polynomial function equal to 0. Step 2, factor. But what can we use to factor this? I can no longer factor out x because x is here, but it's not present on the last term, right? So here the greatest common factor is just 1. It's a trivial greatest common factor, right? Nothing is gained by factoring out 1. So instead, you gotta recall this other method that is very good for 4-term polynomials, right? When you have 4 terms, think of factoring by grouping. Factoring by grouping, Professor, how is that done? Remember, you learned before in previous courses, right? Factoring by grouping is all about grouping. You group the first 2 terms, these 2. You factor out the GCF here, or the greatest common divisor, also called. Greatest common divisor, you take the power with the smallest exponent, right? I'm gonna write here smallest exponent, 2, right? This is your GCF. Factor that out, x squared out. What is left? X squared into x cubed is just x, right? Plus x squared into 3x squared, x squared into x squared is 1. This is just 3. Done with this part, right? Now we're gonna factor out the last 2 terms. Group the last 2. What is the greatest common factor here? Greatest common factor is 1, right? 1. But remember, whenever that happens, since this is negative, you have to attach to your greatest common factor the negative sign, right? You have to factor out -1, not just 1, because you want this to be the same, right? Yeah, very good. So -1 into negative x is what? Negative into negative positive, 1 into x is just x, -1 into -3, negative into negative positive, 1 into 3, 3. Perfect match. Look, x plus 3, right? Once these 2 guys match, you just do this. You pull this out right there, the same. It's like a new greatest common factor, right? There you pull out. This into this cancels, this x squared is left. This into this cancels, -1 is left, right? Yes. But now, guys, turns out this can be further factored, right? Further factor. How? Well, remember, there is this technique called factoring the difference of 2 squares. The number 1 is the same as 1 squared, right? Because 1 times 1 is 1. So if you write it this way, this allows this other factorization. X minus 1 times x plus 1, right? This is using difference of squares. Let me write here on the side a note so nobody gets lost here. Recall a squared minus b squared factors as a minus b times a plus b, right? It's called factoring using difference of squares, right? Recall this. That's what I use to factor this completely, right? Maybe I can write here factor completely, as much as you can, right? Yeah, okay, great. All right, now the third step is this: set each factor containing the variable equal to 0. So x plus 3 equal to 0, x minus 1 equal to 0, and x plus 1 equal to 0. From there, guys, subtracting 3 in both sides here, you can get, after canceling these 2, that x is equal to -3. That will be our first 0, right? The first solution. X equal 1 will be our second 0, right? And x equal -1 will be our third 0, right? This 3 zeros there. So conclusion, the zeros are of, what was the function? F of x, right? The zeros of f of x are, the zeros of f of x are, and we just list them all: -3, 1, and -1, right? These are the 3 zeros. Maybe I can put n here. Yeah, and that's all, right? I leave it's tricky. The factorization requires factoring by grouping together with factoring the difference of two squares. So be careful there, guys. So now let me show you an example, right? One example. But before we go over an example, guys, I want to emphasize this again, right? These guys, -3, 1, and -1, they determine the x-intercepts. I can say that then the x-intercepts of this polynomial function f of x when graph will be this guys, -3, 0, 1, 0, and -1, 0. Professor, how come this becomes the x-intercept? Well, let's graph it, right? Let's graph it. So we have this tool, y equal x cubed plus 3x squared minus x minus 3. A better behaved graph, right? The other one was went out of our scale, but this one clearly you can see is showing that the first x-intercept is -3, 0, as we stated here, right? This guy, -3, 0, first x-intercept. Second x-intercept, -1, 0, is here, -1, 0, right? And the third x-intercept, the third point where the graph meets the x-axis, 1, 0 is here, right? 1, 0, right? Try to remember this, guys, because there will be a moment when we will have to use this. Whenever you cannot factor, use this graphing tool to find your x-intercept, therefore your zeros, right, of your polynomial functions. Great. Okay, now I want you to practice on this form, okay? Then we'll talk about this. Okay, so let's practice here. Yeah, can you try this one? I think it's number 13. Yeah. This guy. Let's try this. Could you figure out the zeros of this using step 1, step 2, step 3? Hint, right? Step 1, set whatever the formula is that defines your polynomial function, set it equal to 0. Step 2, factor, right? Factor, and then set each factor containing the variable equal to 0. Factor. Yeah, very good, very good. I can see people already posting. Very good, let me see. Jing. Excellent, excellent. You got it. Very good, very good. Yeah, work on this, guys. Very good, very good. Very good, guys. So, and try to remember this on your when you do your homework. Okay, you will have to factor. You have to show your solution. If they are repeated, you may have to deal with multiplicity. We will talk about this in deeper detail next. All right. So here, I have 1, 2, 3, 4 terms, right? And I noticed that I cannot factor out x because x is not present on the last term, the constant term, right? So I'm gonna follow a factorization by grouping. Factor using factorization by grouping. Okay. Factor using factorization by grouping. By grouping. All right, so what is that about? Well, you group the first two terms and you group the last two terms and you factor the first two terms and the last two terms independently, right? Here, for example, you notice that for the first term and for the second term, the greatest common factor is just x squared. Why x squared, Professor? Because fx squared is the one having the smallest exponent, right? Smallest exponent x is 2. So GCF x squared. If you factor out x squared, what is left inside here? Parentheses, x squared into x cubed, subtracting the exponents is just x to the first power x, right? Plus x squared into 4x squared. X squared into x squared 1. This is just 4, right? For this part now, greatest common factor for 4x and 16 is the number 4, right? 4 goes evenly into 4, evenly into 16, right? But now, guys, remember, there is a rule. If there is a negative sign in front of the coefficient of the third term, factor that out together with your GCF. So factor out negative 4. Negative 4 into negative 4x, negative 4 into negative 4, 1. This is just x. Negative 4 into negative 16, negative into negative positive, 4 into 16, 4, right? Perfect match. Look, x plus 4, x plus 4. Take this out, x plus 4, treat it as your new greatest common factor, right? And what's going to happen here is this guy into this guy, look, this cancels, x squared stays here, right? X squared, great. Minus, minus. This guy into this guy, look, this cancels, minus 4 stays, right? And that should be equal to 0. But now notice that when you look at this factor can be written as follows, x squared minus 2 squared. 2 squared is 4, right? I'm writing it in this form because I want to use this fact. The difference of two squares, a squared minus b squared, factors as a minus b times a plus b, right? I want to use this. So this is going to be x plus 4 times x minus 2, right? You just pick up the basis, right? You don't care about the exponents. X minus 2, the difference, and then multiply by the sum of the bases, x plus 2. Very good. Equals 0. Next step, set each of the factors contained in the variable equal to 0. From there, you should be able to extract your zeros, right? Zeros. Look here, subtracting 4 in both sides, x equal negative 4, first 0, right? Adding 2 to both sides, or taking simply the opposites, right? That also works, right? Subtracting 2 in both sides, x equal negative 2, the third 0. So there are 3 zeros, right? Negative 4, positive 2, and negative 2. These are the 3 zeros. So go back. The one that is telling you that, is negative 4, 2, and negative 2 is the first one, right? So negative 4, negative 2, and 2. Very good, guys. Very good. Excellent. Great. Okay, so use factoring by grouping if needed. And you may say, right, Professor, what if we cannot factor? That will come later. Later, we will give you other techniques, more sophisticated whenever you cannot factor, right? But I gave you this technique, and also I show you that with the graphing tool, you can catch the X-intercept. That's another way. Now let's look at the relationship between the zero of a polynomial function and the X-intercept when you look at the graphs of the functions. graphical behavior of polynomials at X-intercepts, okay? So let's try to catch this. It says, if a polynomial contains a factor of the form x minus h raised to p, let me make it a little bit bigger. Yeah, that's better. The behavior near x-intercept h, right, this guy, is determined by the power p, by this exponent. We say that x equal h is a zero of multiplicity p. Remember, I talked to you about multiplicity, right? If instead of 1, which is a very common situation, right, for this exponent, you find here 2, as we saw before in the example when the zero number 5 was repeated, right? Then you will say that that 0 has multiplicity p, right? Could be multiplicity 2, multiplicity 3, okay? But now mathematicians discover that the graph of the polynomial function will touch x-axis at zeros with even multiplicity. So if the multiplicity is even, the graph will touch the x-axis and then will go away. Maybe this way, maybe this way. Otherwise, the graph will cross the x-axis at zeros with odd multiplicity, right? So if the multiplicity is not even, it must be odd, right? So in that case, it will cross the x-axis this way, perhaps, maybe this way, right? All right. Now, for you to understand this, let me show you this example. Example 1 says, given f of x equal x plus 4 times x minus 3 squared, they're giving you here a polynomial function in factor form, right? They're asking you to find the zeros of f of x first and state their multiplicities. Okay, let's do that. And then let me show you how these multiplicities are related to the graph of the function, okay? Now, so f of x equal x plus 4 times x minus 3 squared, right? I have the polynomial function factor, so I just go straight to the second step. Well, the first step says this, right? Set this equal to 0. But the second step says just set each factor containing the variable equal to 0. So we gotta set these two equal to 0. From here, subtracting 4 in each side, I get x equal minus 4, one of the zeros, right? From here, this is a square. Remember, this guy determines the multiplicity, right? The multiplicity. So you can say that this will be equal to 0, x minus 3, but with multiplicity 2, because this is x minus 3 times x minus 3, right? You follow, guys? Yeah. So you still set x minus 3 equal to 0, right? And you say, aha, the solution will be x equal 3, but with multiplicity 2, right? With multiplicity 2, because it will appear twice, right? This is just this. I want you to see it. Yeah. Right? Twice you are setting it equal to 0 indeed, right? So this will be x equal 3, but with multiplicity 2. Now, how is this related to the graph of this? Well, notice the following. If you bring up your Desmos graphing calculator and you graph this function, right? I'll show you here. Y equal, between parentheses, x plus 4 times x minus 3 squared. Notice that the graph, let me make it smaller so you can all can see it. Yeah, this is better. Notice how the graph, this is, move this here. The graph is crossing here at x equal minus 4, consistent with the fact that the exponent here is odd, right? It's the number 1 odd. But notice how then it just touches and goes away when the 0 is 3. Look, doesn't cross. It just touches the x-axis and goes away, right? Yeah, and that is a reflection of the fact that the multiplicity is even, the exponent there is even, right? So multiplicity even, graphically speaking, shows this, right? Touches and goes away. Whereas multiplicity odd crosses, right? Yeah, I want you to catch that. All right, guys. So now I want you to do this sort of on your own here. It says here, find the zeros of f of x, right? By looking at this graph, whose graph is shown below, and write a possible equation for f of x. So can anyone find the zeros and then figure out an equation for this? Let me give you the units here. This has to be 1 unit, okay? This we type here is 1 unit here, and this one 1, 2, 3. Let's say it's 3. Let's say this is like this, 2, 3. This is like this. When you do this on your homework, you will see the graph clearly, right? Yeah, and kind of before, to remind you, right, for you to make the connection, the reason why here, remember, it was crossing at -4, remember, like this, crossing was because of this odd exponent 1, right? At -4, it crossed the graph and then crosses, right? And this one touches and goes away, was because this was even, right? So, so what would be the zeros of the polynomial function and then some possible equation? Jing. Very good, Jing. Excellent. Let's write it down. So x minus 1 square. Yeah, but notice, Jing, all the zeros are crossing, right? Are crossing. None of them is just touching and going away, right? This is touching and going away, but all of them must cross. So try to make them cross. Okay, so yeah, let's do it together probably. And I have another one there where I can show you more about this. Okay, so let's do this together, right? Notice that this is crossing, right? Crossing. So let's do crosses. Crossing also, right? None of them is touching, right? Crosses. There's another crossing, right? None of them is touching. So no reason to believe that they should have an even multiplicity, right? Because they're all crossing. Very good. Yeah, very good. Yeah, very good, Jinji. Now it's fixed. Very good. So look, notice the zeros of f of x are first, right? Are. Let's list them, right? They're going to be -1, 1, and 3, right? These are the zeros of the polynomial function, right? Now, I invite you to do this backward thinking, right? If these are the zeros, look here, they came from some factors, right? They came from some factors set equal to 0, right? So the way you construct this factorization, and therefore a possible equation for f of x, is this. Take the opposite of this. Opposite. Right? Opposite of -1 plus 1. Opposite. Yeah, it's tricky, guys, I know, but it's the way you do it. Opposite of +1 minus 1, right? When you set x plus 1 equals 0, you will get x minus 1 as a 0, right? So you got to do it backwards. So 1 here, -1 in the factorization. 3 here, and the factorization, -3. So this should be a possible equation, right? And now these guys as coordinates, they are negative 1,0. This is 1,0, right? A lot of things going on there, 3,0, right? But the zeros are just the first coordinates, right? Notice zeros are just this, this, and this. These are the point, the x-intercept, right? Maybe we should emphasize this here. X-intercepts. Yeah, and this will be the equation, right? What is a possible equation? One possible equation should be this. We say possible equation because there can be others. For example, if you multiply this by 2 is another equation, right? But the simplest probably this, right? That's why they are asking for the possible equation. And this is it. Yeah, take the opposites of the zeros to construct your possible equation, right? That's the idea here. Okay, I have another one here. And this is going to help you in your homework, guys. Try to follow, right? The zero of the and possible equation of x. Yeah, we did here. It's just this, right? Let's copy here. R minus 1, 1, and 3. And the possible equation is this. Plus 1 times x minus 1 times x minus 3. Yeah, that's a possible definition for the function f of x. All right. Now, example 3. This one, look, is showing this curve crossing, but then this curve touching, right? So can you figure out first the zeros, right? As a hint, this one negative 1, this one 1 here, 1 unit to the right, 1 unit to the left. Figure out the zeros first, and then the possible definition for f of x. Yeah, and then I will make a comment on the degree of the function related to the multiplicities. Let me see. Jing. Very good, very good. Excellent, excellent. Now, correct. Yeah, very good, very good. It's tricky, guys. I know it's like backward thinking, but we're gonna get used to this. Yeah, let me go over this and I will comment on the last fact. Okay, clearly here, let's use this color. The graph is crossing, so it crosses. But here it's not crossing, right? It's just touching, sort of kissing the x-axis and going away, right? Just touches and goes away. So this one touches, bounces off, right? Touches x-axis and bounces off. And bounces off. Right? That's the idea. It doesn't cross. All right. So from there, they should be associated with odd multiplicity, right? It's crossing. And they should be associated with even multiplicity, right? Even multiplicity. Now, I want you to look at this fact here, the last one. The sum of the multiplicities is the degree of the polynomial function, okay? So here, odd multiplicity, here even multiplicity, but we know that this is a chair-like function, right? Chair-like This is a chair-like function. Then, since the sum of the multiplicity should give us the degree of the polynomial function, this has to have degree 3, right? It's a cubic function, cubic polynomial function. So this should be degree 1 for this factor associated to this 0, and the factor associated to this 0 should have degree exponent 2, right? Exponent 1, exponent 2. So that 1 plus 2 should be 3. Okay. So then g of x, whose graph is this, right, should be a cubic function. Should be a cubic function. Okay, so that's the conclusion. Then this one should be a cubic function. A cubic function. So the zeros of g of x are going to be -1 and 1 here, right? Pick them up from there for the x-intercept. And a possible equation for g of x is this. Remember, you kind of think backwards. The 0 is -1, but the 0 came by setting this equal to 0. So this guy has to be the opposite of -1, +1. Now the exponent here, this invisible 1, because this is crossing, right? Crossing. Maybe we should put the 1 there. And this, we emphasize, is odd, crosses, right? Because it's crossing. Now the other factor should be this. X, opposite of this, opposite, -1, right? But then this is touching and going away. So this has to be even, the exponent. It's exponent even, so exponent 2. Follow, guys? Yeah, even. And these are opposites, right, of this. Very good, guys. Yeah, so I think with this, we should be okay. Yeah, again, touching, going away, even exponent, crossing, odd exponent, right? The odd exponent. And the sum of the multiplicities equal to the degree of the polynomial function. Yeah, just like in here, right? Degree 1, degree 1, degree 1, 1 plus 1 plus 1, 3, cubic function, chair-like, right? Chair-like function. Should put this here. Chair-like. Okay.